materials, that all of which looks very similar, so we probably should spend as much time as possible on this. I just found out that homework 3 has been graded, and you should be able to see the grades. And I think the solutions will be posted any minute now. So if you have any questions about homework 3, the grades or the grading itself, please contact the TA who graded your assignment. And also there's homework 5 available, and homework 5 roughly talks about, is going to be the one probabilistic learning homework, and it's going to guide you through naive Bayes and implementation of logistic regression and such things. So it's due, I think, on December 8th. You're getting like 5 days more than the usual 2 weeks because there's a break in the middle and such things. Oh, and the one nice thing about homework 5 is that there's an extra credit question because, you know, it's the holidays and stuff. I know that several of you have already started doing the homework, even though we haven't actually covered all the material that we need. People have gone ahead and looked at the material, and I think that's a good idea. At the end of this lecture, you should be able to do the naive Bayes question. And if you've already seen the homework, are there any questions? Yes?
Proving a linear, I think it's called linear decision boundary, is that just saying that the data is linearly separable? That's the first question.
Yeah, so it's it's very similar. Basically, the proof is going to be similar in the sense that if you produce a classifier, then it's linearly separable. If you produce a linear separator. So the constructive proof is similar. The big difference is there's no data set as such. I mean, we're talking about a class of functions being linearly separable or not. You can reduce it to the data set kind of a question by saying that you have labeled every possible example and you have the complete data set. Is that linearly separable? So that's really what it means to ask whether the function is linearly separable.
Okay, so if you can produce a weight vector and some way to classify it, then you can...
So here's how it goes. If you can produce a weight vector that in this feature space makes decisions using the standard sign of the dot product, and that function is identical to the function that we are examining, then the function is linearly separable. So for example, if you take say I don't know, f of x comma y is equal to x. This function is linearly separable because I can just say this, I can give a weight vector. The weight attached to the first feature x, so let's say f of x1, x2 is x1. Then the weight attached to x1 is 1, the weight attached to x2 is 0, and the bias could be some positive, small positive number. Then I have given you a proof that says that this function is linearly separable. So that's roughly what I'm expecting. Are there other questions? Yes.
On the extra credit problem.
Please do that.
On the extra credit problem.
Right.
The last part says, well, you make the Hessian and then you show that it's positive semi-definite. And the last part says, why does this prove that you can get within epsilon?
Right.
Now, you probably don't want an answer of just, well, because this shows it's convex.
Yeah, that's what we can do.
Or you, okay.
That's what
I'm just wondering, like,
yeah,
how much?
Roughly, that's all I'm looking for. Effectively, the extra credit question is asking you to prove that the function is convex.
Right.
And by the way, and it's asking you to prove that the function is convex in a particular way by taking the second derivative. There are other ways of doing it, but this is just one way. Are there other questions about the homework or previous homeworks or such things?
The solutions are up.
The solutions are available now. I mean, you can see them later. Okay, if there are no questions, let's continue where we left off. We were looking in the last lecture. We were looking at maximum a posteriori prediction. And I hope you went back and looked at those slides again, because this was slightly confusing terminology. We looked at map learning and then we looked at map prediction. And just to remind you, map prediction is using the Bayes rule to predict a label for a particular input. So you're given some input x, and you're asked you are asked to compute what's the probability that the label is some particular y for this particular observation. And you can make that prediction using, so that's the posterior probability of the label for the given input. And the map prediction says we are going to predict the label that has the highest posterior probability. And at this point we are assuming that we have these functions that let you compute the posterior probability. How do you get those functions? You have to learn them. One way of learning them is to use map learning. Map learning is a learning protocol which says we learn functions using the Bayes rule, which is on top. You find given a particular data set, you find a function that gives you the highest, which is most probable. And once you learn a function, now using that function you can make a prediction in the form of what is the most probable label given a particular input. Okay, so on top is learning, and here it's prediction. In the linear classifier kind of universe, the way we did the prediction instead of this was, we would say for a particular input we would take the dot product of the features with the weights and take the sign. Here we are saying instead of that we are going to find the most probable label, the label that has the highest posterior probability. And in the linear classifier universe, this part was replaced by all these algorithms we saw, perceptron, SVM, whatever. So on top that's learning, and here it is prediction. So we are still looking at map prediction. And one way of simplifying map prediction is to actually use the Bayes rule to compute the posterior probability of a label. And the way we do that is to basically say that the posterior is simply proportional to the likelihood times the prior. And if we had some way of computing the likelihood, and if we had some way of computing the prior, all we have to do is just try out each label, find the one that has the highest product, and make that pronounce that as a prediction. So effectively, what this means is this is a standard prediction mechanism. It does not really care about how these probabilities came about. All we need now is some way of getting these numbers, getting these probabilities, likelihoods and priors. And this is roughly where we stopped in the last lecture. Are there any questions about this style of prediction?
In last few lecture, we want to maximize margin, so we want to the length of W become very smaller.
Yes.
Is that a kind of PY?
It's not quite, actually, because here we are assuming that the W is fixed. This is not learning, this is prediction. In the maximum margin sort of setting, what we were doing was in the regularizer actually was imposing a preference on the classifiers, on the set of classifiers. This is imposing a preference. This is only during prediction. In fact, PY, if you want to think of an analogy of PY, it's like a bias weight. If all the features were missing, suppose this entire thing was not there, the only thing that will be used for making a prediction is in the linear classifier, the sign of the bias. Right? You have not even seen any features. Here, the P of Y says what's the probability that some label might show up. So this is during prediction. So the regularizer, the max margin regularizer was during learning. So there's a subtle difference. Actually, there's a big difference, but it's not. It uses the same terminology, so it seems more confusing than it should be. Are there other questions? Yes.
In math learning, when we have P of D in the denominator,
Right.
we drop it,
Yes.
it's independent of sketch.
Yes.
Usually when doing this, we write that we apply this rule of total property to
Yeah, but the thing is, okay, so let me,
H
yeah,
P of D not
sure.
H
But let me repeat the question too, so that everyone can hear it. The question was, when we were doing map learning, the way we got to the quantity here was by actually saying that what we care about is P of H given D, and we say this is equal to P of D given H something like this. And then, but then when we are actually doing the argmax, we only look at the numerator. And the reason for that is because the denominator does not depend on H. It doesn't matter which hypothesis you use, P of D is a constant with respect to this argmax. And if I understand the question right, you could have written P of D. I'm just going to continue writing on this slide and look at only the red text, not the black stuff. So this is sum over H. And it seems like there is the H inside, but you're summing over it, you're marginalizing it out. As far as the sum is concerned, it's not a function of H. It doesn't depend on it, so it can be ignored if all you care about is the argmax. Okay, so now let's explore this idea of learning a little bit more. But I want to go over this one example that we did in the last class about map prediction, where we talked about playing tennis. And suppose there is some magic function that that finishes learning. We don't care about how learning happened, but some procedure went out into the universe and gave me how to produce these numbers, which says what is the probability, and what we care about is will I be able to play tennis based on, or it will predict whether I should play tennis or not based on the temperature and the wind. And if we care about argmax of the product of the likelihood and the prior, so we need these two tables, likelihoods and priors, assuming a certain class of distributions. So the prior is simply a probability of the label. So it basically has two values, a probability for yes and a probability for no, and they should add up to 1. And that's simply saying, in the absence of any information, should I play tennis or not? The likelihood says, on days that I do actually play tennis, what is the distribution over the observations, over the temperature and the wind? On for example, the first row there says, on days that I play tennis, that is, given that play tennis equals yes, the probability that the temperature is hot and the wind is strong is 0.15, and so on. So you basically, your likelihood has to be able to produce one entry for every assignment of the feature for every label. So just as an example, say today, well, clearly not today, but say on some day the temperature is hot and wind is weak. Now we want to know what's the probability that, or actually we don't care about the probability, we care about should I play tennis or not. And if we care about the map prediction, what we are asking effectively is what is argmax of play given h comma w, which is the same as argmax of h comma w given play times probability of play. So you have the likelihood and the prior. And we have specific values of h and w here. I mean, these are basically just values of those two features. And all we have to do now is try out every possible value of the one variable here that does not have any values, which is play. So we try play equals yes. We have all the probabilities that we care about in these tables, and we try out play equals no. We compare the two of them, and we say that yes has the higher score, so the prediction is yes. This is our maximum a posteriori prediction. The name is basically the name gives away the algorithm, maximum a posteriori. So you maximize the posterior probability. You find the label that maximizes the posterior probability. That's your map prediction. Questions? Yes?
Are we going to see methods when, like, these variables take a finite set of values? What if one of the variables were continuous, like wind speed?
Right, so basically all you need is a different probability distribution that can allow a infinite support. In fact, one of the questions in your homework, which I don't think certainly we'll not get to it today, talks about a Poisson distribution, which allows infinite support. But just for sake of explanation, I'm going to primarily only use Boolean or finite support.
So do we apply an assumption about the underlying distribution?
Oh, excellent question. Absolutely we do. In fact, this is really the most important decision that we have to make when we are building probabilistic models. What's the underlying distribution? In fact, if you think about it, we did that twice so far. When we did this kind of a silly example about beads being broken, we assumed a certain distribution. When we looked at regression, mean square regression, we assumed that the error was Gaussian. So every time we are building a probabilistic model, we are basically required to make an assumption that effectively says, here's how I believe the world works. And then you try to find parameters of that distribution that maximize the likelihood or posterior probability. That's basically learning. That's a good observation, and we'll see more concrete instantiations of that as we go along. But before actually thinking about specific probabilistic models, I'm going to argue something that I've been arguing throughout the semester. Learning is impossible. And this version of the argument looks like this. Suppose you have this is a table that we actually saw when we were playing decision trees. And say you're given this data set with 14 entries. There are 4 features: overcast, outlook, temperature, humidity, and wind. And you're supposed to predict whether, based on these things, you should play tennis or not. Now, let's look at a kind of a very simplified version of this argument, just something that's basically a counting argument here. What is the prior probability distribution over all possible assignments to the label? It's just some distribution that is a function of that's a function of the label space. So for every label, you need some number, and it's a probability distribution. And in this data set, this is basically just a single number. Why 1? If I tell you what the probability of play equals, if I tell you the value for this, is that enough? Do you have the complete description of the entire priors? Why? Right. So the probability of play equals minus, so let's say this is equal to p, and this is equal to 1 minus p. So this requires me to produce one number, just one number. Okay, that's easy. Consider the likelihood. There are 4 features here, and for every value of the play label, so the likelihood simply asks what's the probability of outlook, comma temperature, comma humidity, comma whatever the W was, given that play equals something, either plus or minus. When play equals plus, you need you need a number for every possible assignment of these 4 features. When play equals minus, you need a number for every possible assignment. Basically, the only freedom we have is we don't need every possible. We have the allowance of not assigning one of those things, because just by if we have, so for example, there are 2 power 4. I think these are all Boolean, so there are 16 different values that these things can take. Actually, not 16. I remember that it was, yeah, these things are 3. So 3 times 3 times 3 times 2. Those many different unique rows are possible. So that is 27 times 2. 54 rows are possible, and we are observing 14 here. And what we need is for every one of those 54 possible feature vectors for each label, we need a probability, right? So we need to say that what's the probability of every assignment of this, say when p equals plus, probability of every assignment of this when p equals minus. We can get away by not specifying one of those numbers, because we know that all those 54 numbers should add up to 1. So if we specify 53, that's good enough. But that's all we have. Basically what we have, if all these features were Boolean, we need an exponential number of numbers, exponential number of parameters to learn. In this case, 54 doesn't seem like a lot, but when you move to d dimensions, things get really messy. Suppose there are k labels instead of 2 labels. Suppose the output can take k values. Then you need k minus 1 numbers for the prior, because if the last one can just be 1 minus the sum of the rest. And if you have d-dimensional feature vectors, and let's say they are all Boolean, you need a value for every feature vector given every possible label. This is roughly k times 2 power d number of parameters. Questions? Does this seem like a reasonable argument that I'm making? Does it seem like an unreasonable argument? And this is important, because this is really what drives the next step. And in fact, a lot of probabilistic models, the reason we have all these different models, and the reason many different kinds of probabilistic models exist, is because of this computational argument. So I want this to be very clear.
So then we're saying that this many parameters would be required if we make no structural assumption of
Yes.
the probability
Yes.
distribution. If we just let it be whatever.
Yes. In the absolute worst case, in the completely uninformed case, these many numbers are needed. If we make without any other assumptions. Yes. Is that? I'm going to continue ahead, but please, if you feel that this is an unreasonable argument, you can come back anytime.
This is if the feature vectors are Boolean.
This is if the feature vectors are Boolean. If the feature vectors are not Boolean, then
It'll be larger.
this number changes. Yes.
So I don't know where the D comes from, but what's the K?
K is just the number of labels. Typically we are doing Boolean, so k is 2. But if you do multi-class, then k becomes whatever the number of labels you have. But even for k equals 2, this is an unreasonably large set of numbers. So, what's the problem? I mean, so what if we have 2 power d parameters? You know, we have large. I mean, memory is free, so we can store these things. So, what's the problem? Think of all these. Think of the ML-related concepts that we've been thinking about, and think about why this would be where this would hurt us. A related question. What's the problem if I have, if I train, say, a linear classifier with 1 billion features? Okay, that's one problem. Also, is there another? I see a.
You have to go through all those to predict, like in case we have to make a prediction.
Oh no, but during prediction you're given one of these rows. You're given a particular thing, so you just have to pull out one of them. So prediction is always going to be, in fact, prediction will be much easier. All you have to do, prediction is literally just lookup. You just have to pull out that one row, compute the probability of plus, say the input is this row. You have to compute the probability of this row given plus, that will be the likelihood, similarly minus, and then multiply both each of them with the priors, pick whichever one has the higher value. So prediction is going to be very, very easy. Exactly. So the sample complexity will kill us. A general lesson in machine learning is if you have more parameters and if the number of parameters you have to learn is high, or in other words, if the model becomes more complex, then it can pretty much fit anything. So it will overfit. Another way of saying the same thing is your sample complexity is going to be very high, because in order to actually learn the right function, you need a huge number of training examples. Because you're just not going to get enough examples. For example, with linear classifiers, if the dimensionality is 1 billion, there is definitely the curse of dimensionality issue. But beyond that, there's a problem that the sample complexity is going to be very large. So, general lesson, be slightly skeptical of classifiers that are really, really, really large, unless you have very good evidence that, again, it goes back to Occam's razor. So, how do we do this? There was a suggestion about this before, so what can we do? What did we do with sample complexity, with really complex hypothesis spaces? How did we get around the fact that learning with large hypothesis spaces is not going to help us? The one trick that we have.
You make an assumption or restrict the...
You make assumptions. If you can't solve a difficult problem, you assume that the problem is simpler and try to solve it. So the answer is you make, in this case, because we are in probability land, we make independence assumptions. We assume that certain things are independent of each other. So let's look at just a detour about conditional independence. So let's say you have a few random variables x, y, and z. Just remind you, and you must have seen this before, but I just want to remind you, 2 random variables x and y are conditionally independent of another random variable z if the probability of x comma y given z can be written as the product of each of them, each of the conditional probabilities. Or another way of saying the same thing is the probability of x given y and z is independent of y. These two are equivalent. And this is one of the most important tricks in the toolbox when we are building probabilistic models. You assume if computational complexity hurts you with respect to say learning or with respect to sometimes even actually prediction becomes complex, you just assume that you are searching over a space of models. So this is basically a restriction over the set of all probability distributions. Probability distributions that are conditioned, that have this property are a very special set. So we assume that the distribution, the likelihood that we are trying to learn, has some conditional independent structure in it. In particular, if we have D features and we care about modeling these likelihoods, what we could assume is that every feature is conditionally independent of every other feature given the label. Having seen the label, all the features get disentangled. So how many, in equations that simply says the probability of this feature vector, of observing this entire feature vector, which is basically just an object, is simply the product of the probabilities of each of its components. And this is a conditional probability. So sometimes you hear the phrase class conditional probability distribution. So this is the class or the label, and this is the distribution that is conditioned on the class. So we could, if we assume that the class conditional probability distribution has this conditional independent structure, then we are actually in a much, much, much better place, because each one of these. So if we have booleans, so let's take just x1 given y. We have a table that looks like this: x1 and y. When y is true, when we need x1 given y equals plus, and probability of x1 given y equals minus, and let's say this is plus and minus. So you just need 4 numbers. Actually not even 4, because these two should add up to 1 and these two should add up to 1. So just need 2 numbers. And you have D such features, so you just need 2 times the number of features. So 2D, O of D parameters. So this incredibly strong independence assumption has let us go from a setting where we needed an exponential number of parameters to a setting where we only need a linear number of parameters, linear in the dimensionality. Questions? Just to give names to these things, this assumption is called the naive Bayes assumption. It's Bayes because it's a probabilistic model. It's naive because it makes this incredibly strong assumption. So, are there questions about this? Yes.
Has anyone really asked how sensitive it is to how sensitive the conclusions are to that assumption? As in, let's say that you knew that, like, maybe the oracle tells you this assumption's not correct,
Right.
but it still basically gets you very close to
That happens quite often. In fact, there were a few papers from the late 1990s that tried to answer that question, early 2000s also. And there are different ways of answering that question. It so happens that for certain classes of problems, the naive Bayes classifier just works very well, and it works disconcertingly well, even when you know that the assumption is not satisfied. And there are a few attempts at explaining that. One, for example, there are many different explanations. One of the explanations is that if you think of the space of all probability distributions, the set of all probability distributions that satisfy the naive Bayes assumption, which is a subset, is very densely distributed across the space. So for any probability distribution, you'll find one that's nearby. And that's kind of a cool statement. Another way of thinking about this is, on one hand, you will make mistakes because of high sample complexity. You're just not going to get a good enough classifier, which is overfitting. Naive Bayes goes the other way. you have an extremely impoverished set of functions. You're willing to underfit, and so you're trading off overfitting for underfitting. And is that a good enough trade-off? Seems like in practice, in certain problems, it is. Now, in your homework, the first question asks you to stare at naive Bayes and come up with these probabilities for a certain function. And I don't want to give away the answer, but I can tell you that interesting things happen for that function. So, if something surprising does not show up, then you should be surprised. Right. So, just to put all of this together, the naive Bayes classifier is a probabilistic model. Notice that at the end of this, basically we still are predicting probabilities for labels given features, and all we need to do is to come up with a way of defining the likelihood function. And the naive Bayes classifier says every feature in this likelihood function is conditionally independent of all other features if you observe the label. So the likelihood is exactly that. The likelihood is the conditional probability of the features given the label, and the naive Bayes assumption says that particular object, P of capital X or bold X, the feature vector X, given the label, is simply the product of individual probabilities. So all we need here now is to completely specify this classifier. All we need is a set of priors, one for each label, and a set of class conditional likelihoods, one for each feature. If there is some magic box that gives me these numbers, then I can go around making predictions. And the prediction is fairly simple. We'll use basically it's still map prediction. We're going to predict the label. So I'm using this notation H just to tie it to what we did before in the class. H is a function. It's a function that takes an input X and produces a label. And the naive Bayes classifier takes the input X and computes this product for every label, P of Y times P of X given Y, and finds the label that has the highest one. But that's not all. Because we have this naive Bayes assumption, this product is simplified. It's this term here, the likelihood is exactly this. We are assuming that it's equal to this product. Okay? And this is the classifier. The naive Bayes classifier is exactly this. It takes some input X and produces a label using this rule. So the function H is completely specified if I give you the priors and the likelihoods. And now we can think about learning. For learning a naive Bayes classifier, all we need is to figure out these probability functions. And the learning setup is the same as always. You're given a data set with, in this case we are still in supervised learning, so you're given a data set consisting of labeled examples, and we want to learn this classifier in a probabilistic way. Just to make sure that we're talking about the same thing, let me write down H and V of X is so if I use J for this, so let's just use J. So if I'm able to get you these numbers, so this is this here and this is this quantity. So all I need for learning is to produce somehow, take this data set and produce functions that can give me the probabilities. How do we learn? What criterion do we use to find a good classifier in the probabilistic universe?
Your H of X is output of the classifier.
H of x is the output. Yes. Yes, the label. In the linear classifier world, h of x would have been sine of w transpose x. And there, in the linear classifier world, learning was search over the space of all w's to find the one that maximizes some criterion or minimizes some criterion. In the probabilistic, in the naive-based universe, h of x is simply this collection of probabilities, or actually collection of these probability functions. Learning is to search over the space of these collections of functions and find the one that does what. How do you know whether, how do I know that this collection of probability functions is better than another one? What criteria do we have? What's the probabilistic criterion for learning classifiers?
Most probable hypothesis.
Map. Maximum a posteriori learning. So, what we're going to do now is, I'm going to just give you the maximum likelihood, which is similar to maximum a posteriori. What we have on top is map prediction. We are going to predict a label. And now we are going to use a probabilistic criterion for learning the predictor itself. So what we'll do now is we'll search over the space of all h's. H is simply a collection of probability functions. We'll search over the space of all h for the one that maximizes the likelihood of the data. And this is the first time we are actually going to go through the gory details of how to do maximum likelihood learning. So, feel free to stop me whenever, anytime you feel that this is an overload of terminology. The first thing that helps us in this is this assumption that so the game we are playing here is, we are given a data set consisting of examples, L examples, and we want to find that classifier that is most likely to have produced this data set that we are observing. And because we know that every feature is independent, every example is independent, we can just say the probability of the entire data set, given the hypothesis, is simply the product of the probability of producing each example, given the hypothesis. So this term here inside the box is simply asking, suppose I give you a certain classifier, a certain set of probabilities, likelihoods and priors. What probability would this particular classifier assign to the example that I'm holding in my hand right now, the xi, yi? You take the product of all those things, and that is simply asking what probability would this particular classifier assign to this data set that I'm holding. And maximum likelihood classification simply says, find the classifier that will give the highest probability to this data set that you're observing. That's the intuitive explanation. So from now on, it's just basically a lot of algebra. I'm going to fill up this slide with math, but it's mostly algebra. There's not much in terms of technically difficult stuff. We've done the difficult part already. So, because we are doing maximum likelihood learning, we are just trying to find the classifier that maximizes the product of the likelihood of every example. That's the first expression here. And going from here to here is basically just applying the definition of conditional probabilities. Because we know that P of, say, A, comma B is I've done nothing here. I just literally going from the first step to the second step is literally just applying the definition. The only minor difference is things are conditioned here. So given C, it's instead of AB, it is given C. And then you have to condition everything. Times. Okay? But now, we have to somehow come up with a way of producing this, we can expand this. The first term here, the second term, P of yi given h, yes?
I just want to make sure I understand. So in the inside of this product,
Right.
we're saying what is the probability that we predict yi from xi
No.
given h?
Aha, in fact, it's not that, and that is actually an excellent observation. We are not asking what is the probability of predicting the label given an example. We are asking what is the probability of predicting this pair of, so think of, in fact, what we are doing here, the naive Bayes classifier gives you a probability of generating labeled examples, both the features and the examples, the xy pair. When we get to the end of this discussion, I'll actually talk about the difference between these class of models that assign a probability to this pair versus, which are called generative models, versus another class of models which assign a probability just to the label given the x. Those are called discriminative models. Naive Bayes is an example of a generative model. So for now, we are just trying to assign, we are asking what is the probability that this example can exist in nature. By example, it's both the pair, both elements of the pair. And so yes, that's a very subtle point, so good observation. Okay, now we've not, so far, everything I've said, nothing I've said use the naive Bayes assumption, because we still have this probability of the bold xi, which is the entire feature vector. But now we can apply the naive Bayes assumption on the features, because we have made a modeling choice. The first modeling choice that we had was to say that every feature is independent, so probability of the entire feature vector is simply the probability of the product of the probabilities of each one given the label. Okay? So what we care about, notice, is we have an argmax here. And H is simply this big bucket of all those, any parameters that are needed to describe the probability distribution. We still haven't even specified what shape the functions will take. But even before that, we can do a little bit of cleanup. How do we proceed? Any ideas? I want to solve this maximization problem over a large product.
Take the log.
Take the log. So we take the product and make it into a sum, because log is an increasing function, so argmax is not going to change. So we just take the log. So what the maximum likelihood classifier, according to naive Bayes, is simply that those set of probabilities which are all contained inside this bucket called H, which maximize this giant summation given the data set. The first term in the summation is 1 over each example, it corresponds to this product. And this is simply the summation over each feature. Okay, what now? Have we solved the problem? We haven't, because we need to make another assumption now. And this assumption is, so notice that I'm basically just throwing out assumptions. Every time I get stuck, I'm throwing out an assumption, and that's generally a reasonable strategy, it seems, in building predictors. If the math doesn't work, make an assumption that makes it so that it works. But at this point, we don't need, it's not an assumption that talks about the math working. We are going to make a modeling assumption. So far, I'm just talking about these vague probability distributions. I have made no assumptions that these distributions have a certain functional form. I've made no assumptions that they are Bernoulli or binomial or anything. So let's make that assumption now. But thing is, this group of classifiers, they are all called naive Bayes, independent of what assumption you make about the probability distribution here. So just as an example, so for example, this classify. So this probability of xij given yi comma h. If suppose y is plus comma minus, plus or minus, if y can either be a plus or a minus, that can be probability of xij given yi equals plus, and we also need probability of x comma xij given, we need these two numbers. But still, we don't know what these xij's look like. If they are Boolean, then all we need is one number for this, xij equals plus. Then we can derive the value of probability of xij equals minus. So basically, we just need one number that specifies this. If on the other hand, this was actually a real number, we need a probability distribution that can give you a probability for any assignment, any value of the xij. So we can ask, what is the probability that this particular feature, say the temperature, is at 70 degrees, given that it is snowing? What's the probability that the temperature is 70.1, 70.113? So we need a probability distribution that can support real numbers. One example of that, which is actually very convenient, would be, we could assume, if this was a real number, we could assume these are Gaussians. If this is a binary, then we can assume that it's a Bernoulli. So let's take the simplest example. Yes?
Could you maybe estimate a distribution, like for example, use a kernel estimate of the distribution?
We have to. In fact, that's really what learning is. Basically, the learning problem amounts to estimating the probability distribution. We're going to work through a very, 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 very simple version of this. So, suppose we have two labels, 1 and 0, plus minus 1, 0, true, false, whatever. And let's assume that all the features are also Boolean. Then the prior is simply, as I said, one number. We need some way of knowing what's the probability that the label is 1 or probability that the label is 0. The likelihood consists of two numbers for every feature. So let's go over this one row at a time. When the label is 1, so I'm talking about this term here. When the label is 1, we need to be able to say what's the probability that the jth feature is 1. Let's call that aj. That gives us the probability, and just by specifying this to be aj, we get 1 minus aj is the probability that that particular feature is not 1. We also need to say what is the probability that the jth feature is 1 when the label is 0. Let's call that b. So we have two numbers for every possible assignment to the, we have two numbers for every feature. So we have 2D numbers. It's the same thing that we were looking at before. I'm just using terminology. I'm just giving them names, because what's important is this H, the bucket that basically that I said gives you that specifies the probability distributions, is simply a big bucket consisting of the P's, all the A's and all the B's. Because if I give you values for those numbers, then you should be able to specify what the probabilities are. So the learning problem is basically just using a data set to find values to P, A and B. Questions?
If one of the variables were continuous, would we replace with the density function?
Yes, yes. If the variables are continuous, then it will be replaced with the density function. Even then you have a choice of which density function. If the feature is, say, can be natural numbers, then you have a choice of a probability distribution over natural numbers. If the feature takes, say, k possible values. Then you can pick a multinomial distribution, which here takes 2 values, so you can take a binomial distribution. So this is a really, really important choice that you have. You're basically making a choice as to what the probability distribution is that generates the data. Here I'm assuming that the prior is basically a coin toss. So here's another way of thinking about this. The prior is a coin toss. So what you do to generate the data is first you toss a coin. If it's heads, you say that the label is +1. Then you have a complete set of coins which are labeled A and a set of coins labeled B. If the coin toss for Y comes up to a plus or it comes up to 1, then you go to the collection of coins called A. You have B such coins. You toss each one of them separately and you take the state of those coins and that's your feature vector. So that gives you your entire example. If the prior coin, first coin on top came up to a minus or came to a tails, then you go to this other set of coins which are called B and you toss the entire set. Notice that here, this is actually exactly that independence assumption. All these coins are independent of each other. Given, if I tell you which coin was tossed at the top, the prior, then all the A's and the B's are independent. So here you have, effectively, you have 2D plus 1 coins. Right? And if the learning problem is simply to learn what are the biases of all those coins. That's another way of thinking about this kind of a classifier.
Maximum likelihood you say priors and not
That's the prior over all classifiers. This is the prior over the label. So in maximum likelihood, we assume that the prior over the classifiers is uniform. Meaning, what we are saying is, we don't know what the bias of the coin is, and we have no preference over the biases. The map prediction says, map prediction requires a prior over the label. Is the process that generates, this is called a generative process. Is that, does that make sense? The generative process that we have, that we believe is creating the data when we are using the naive Bayes assumption. So now the question is, how do we learn all the P, A and B? In other words, how do we learn the biases of these coins? And I'm going to introduce a little bit of a notation here that actually makes learning a little easy. Or actually this notation is hideous, but it makes the math easier. It's a lot of writing, but it makes the calculus easier. So suppose you have this prior is the probability of y being 1 is p, and the probability of y being 0 is 1 minus p. And say I'm giving you a particular example, x comma y, or xi comma yi. This x is an entire vector. Now I want to somehow use the p, and you use the p to replace that first term there. So let's look at by the way, h is simply p, a and the b. The probability of yi, I'm not going to write the h because that's just going to be a lot of writing, is either p when yi equals plus and 1 minus p when yi is minus, right? That's really the definition of this thing. Alternatively, I can say this is equal to p times, so let me introduce this a notation that says, something called the indicator function. The indicator for y is this quantity that is 1 if y equals plus and 0 if y equals minus. Okay? It's just a terminology. And I'm going to use these two things to define probability of y. Probability of yi is simply, it's either p or 1 minus p. We know that it has to be p or 1 minus p because it has to be in one of these two buckets here, those two buckets. So I can say it is p power, the indicator for yi, the pen has a mind of its own. It's p power this times 1 minus p power 1 minus indicator. So I'm going to argue, so let's just get rid of all the lines and stuff. I'm going to argue that this quantity is the same as p of yi. So let's walk through this in a one step at a time. P of yi can either be p or 1 minus p. The indicator is just a way of encoding that choice into a Boolean, into a 0 or 1. If yi is true, if yi equals plus, then this quantity will be 1, which means it's p power 1 times 1 minus p power 1 minus 1. So this disappears, the second term disappears. So if yi is plus, then this product will simply be equal to p. If yi is minus, then the indicator for yi is 0. So this quantity disappears, the first term disappears, and this product simply becomes 1 minus p. It's just a notational trick that lets you do calculus very, very easily. It's a lot of writing, but it actually makes the math a little easier. So I'm going to erase this and bring up the typed version. So what we have is p of yi given h is simply p power the indicator times 1 minus p power the other indicator. Indicator for y equals 0 is exactly the same as 1 minus y equals 1. This is also called the Iverson bracket, and it's actually just some notation that makes solving the argmax very, very easy. Questions about this notation? Because we'll be using a variant of this even when we come to the EM algorithm. So it's important that this is, yes?
Okay, so is the y equals 1 the same as p?
Which one?
The one on the left, can you explain what that is, the p to the y equals?
This one? That
Yes.
part? So think about it this way. The Iverson bracket or the indicator function is simply a function that returns one, that takes a Boolean and returns 1 or 0. It takes a proposition, and if the proposition is true, if the proposition is false, its value becomes 0. So this quantity we know has to be either p or 1 minus p by definition, right? It's a p of yi is, let me write the expanded version of this. So this is the expression that we are trying to capture in one line. So the first term here says when pi equals 1, then multiply to the p. It just so happens when yi equals 1. When yi is 1, this becomes equal to 1 by definition. When yi is 1, this becomes 0. So you have p power 1 times 1 minus p power 0, which is p. When yi is 0, this term becomes, the first term becomes 0, and the second term shows up. So this entire thing, the first term in the product disappears, so you're left with 1 minus p, which is just the second term here. So it's literally just a notational trick that takes this kind of a multiple case definition into a single line definition.
This product is looking more like the Bernoulli.
Yeah, yes, in fact, if you replace these with counts, you get Bernoulli. Yes. Okay. Now here's the ugly version of this that I'm not going to go through in gory detail. Turns out I can write the second expression also using these indicators, but now these indicators will involve two quantities. The probability of x given y comma h can either be or xj given y comma h can either be aj or 1 minus aj, depending on whether y is 1, whether the corresponding feature is a 0 or 1. If the corresponding label is 1, so that's the first row here. If the label is a 0, then it can either be a b, it can be one of the bj's, either plus or either bj or 1 minus that. And this is effectively what we have is a four cases. So probability of xj given yi is aj if yi equals 1 and x equals 1. So let me write this as a table. Yi x ij. We have 1 and a 1 here, a 1 and a 0, 1, 0, 0. So that covers all the cases. So you have four terms in this product. It's exactly the same, and I encourage you to actually convince yourself that this is not a lie. And it's again just a convenient notation. But what that means is that now you can plug in these quantities into the log. The reason we are doing all this is because even in this case it becomes easy to see. When I take the log of this probability, this simply becomes log indicator for y equals 1 log p plus indicator for y equals 0 log 1 minus p. This quantity here. So it becomes a giant summation over log probabilities. And this is actually a much nicer form to do calculus over. So, questions before we go ahead? Yes?
On this slide, what does a comma mean? Is that a conjunction?
Conjunction. It's just and. Yeah, I couldn't fit in conjunctions into this slide, but yes, comma means and. So this is simply saying when yi equals 1 and xij equals 1, then use aj. When yi equals 1 and xij equals 0, then use 1 minus aj, and so on. So the hypothesis function that we remember, that function that we care about learning, is this collection of a, b and p. So what we have to do next is to solve this argmax is to take the derivative of that big function that once you plug in the log probabilities using this Iverson notation, you should take the derivative of this, set it to 0 and compute the value of, you can do one of two things. You can do gradient descent, or you can just try to set the derivative to 0, because when the derivative is 0, you get an extremum. It just so happens for a naive Bayes classifier, taking the derivative of this with respect to p and setting it to 0 gives you a closed form solution. P is the prior. Remember, P is the prior. It's simply saying what's the probability that the label y is 1. If you do this whole complicated procedure for the binomial distribution, take the derivative of that the maximum likelihood function, set it to 0, you'll basically get the following solution. It simply says the probability that the label is 1, the prior probability that the label is 1 is simply go over your data set, count how many times is the label 1. That's the numerator. The denominator is count how many times it's 1 or 0. Just the number of examples. So the probability, the prior probability of getting a label, that the label is 1, is simply the fraction of times that the label is 1. And I know what you're thinking. If you were with me so far, you're going to be like, I could have told you that without this mess. It turns out, internally, you're actually making all these assumptions and coming up with this kind of doing the calculus in your head, and it just so happens that, you're doing it without knowing. Now, if you want to find the Aij and the Bij, A and the Bj, it's exactly the same. Aj is the probability that a particular feature xj is 1 when the label is 1. And that's just the number of times the feature is 1 in the data set for examples that have the label 1 divided by the number of times the example is 1. It's the most obvious thing that you might want to try. If I give you a set of examples and ask you, what's the fraction of times, what's the probability that a particular feature takes a value 1 for label equals 1? What do? You just count how many times the pair 1, 1 occurs, divide by the number of times the label becomes 1. It just so happens that going through this, effectively what you're doing is each feature is independent. You're pretending that every feature is independent of all the others. That's why this count works. Similar thing for the B as well. This, even though I'm not working through all the messy details, because I've done this before, you should go home and try to work out this derivation, because it's going to take up a lot of space, but it's actually just very, very easy math. So please work it out, and it will give you a better intuition of why these things are what they are. So let me give you an example. Suppose I had to train a naive-based classifier for this tennis data set. The prior is the probability that play equals plus. That simply count the number of pluses. There are 9 pluses here. Divide by the number of examples. So 9 divided by 14 is the prior probability of the label being plus. Now we need to learn the class conditional likelihoods. When the label is plus, the probability that the outlook is sunny is 2 divided by 9, because among the examples that have a label equals plus, there are only 2 of them where the outlook is sunny. Similarly, the number of likelihood that the outlook is rainy when the label is plus is 3 divided by 9, and this overcast gives you a different number. And effectively, what we are doing is learning a naive-based classifier. So, learning a naive-based classifier literally just amounts to going over the data and keeping track of various counts. And at the end, just dividing. So, the naive base can be learned just by counting. So, let me summarize what we have. The naive-based classifier makes this extremely strong, naive independence assumption that every feature is independent of all other features given the label. And with this assumption, what we are able to do is to say that we can even prove that learning can be reduced to simple counting. If you have a binomial distribution, then we just derive the example. It can be extended to multi-class and stuff easily. And prediction is also fairly simple. All we have to do is apply the map rule, use the learned probabilities, and find the label that has the highest posterior probability. Questions? Yes.
So how can we evaluate the performance of this classifier?
It's exactly how we evaluate any classifier. How many predictions are right on a head-out set?
Would it be different if, say, the max
the maximum probability is 0.5 versus 0.2.
Right, so that is a good question. So this classifier seems to give you probabilities, not just labels. And if you want, you could use that to somehow evaluate the classifier as well. If, for example, the label plus gets a probability of 0.6, that means the label minus gets a probability of 0.4, versus the label plus getting a probability of 0.99999, there's this measure of confidence, effectively. How far are you from half?
How do we deal with missing that?
That's a good point. This is not going to be very complicated because you just need to keep track of counts. If the feature is missing, you don't count it. Or you could try to be more fancy and kind of give it partial labels, and like we did for decision trees.
Some connection with
Not quite, except for the example.
counting
Well, okay, think about it. I'm not going to answer that question.
What was his question?
He says this is connected to decision trees somehow because in both places we are learning just by counting.
That's what I was going to say. Is there an underlying relationship between this and this?
Not quite, not directly. In fact, there is a stronger relationship between, it turns out, and it seems like, oh man, I'm going too slow. It seems like I won't be able to get to this, but it turns out the naive-Bayes classifier, the decision boundary of a naive-Bayes classifier is linear. In fact, on the class website, I've written a document that actually shows a proof that naive-Bayes is actually learning a linear decision boundary. So even though it has all these connections to all these complicated things, it turns out naive-Bayes is actually a linear classifier. And decision trees are not. So this is a much in fact, it's not even all linear classifiers. It learns a very restricted subset of linear classifiers. The hypothesis space here is very restricted. Couple of caveats. The first one is we made a rather strong assumption that all features are conditionally independent. Given a data set, there's nothing that tells us that this assumption holds. It could hold if you are extremely lucky, more likely if you generated the data yourself. Most likely, more often it won't hold. And the other problem is we are counting. We are estimating probabilities by counting. What if a certain feature occurs only once with a label plus in a data set that has a billion examples? Is that probability estimate robust? What if the data set size is only 3? So sometimes we may not have enough examples to get good counts. I'm going to talk about the first one and stop. Unfortunately, there's nothing that we can do if the features are not conditionally independent. We can hope that the assumptions are satisfied and try to make it work, but there are no guarantees. And in fact, if the naive-Bayes assumption is not satisfied, namely the product of, if the features are not conditionally independent, we have no guarantee. But that argument that I had earlier about overfitting versus underfitting kicks in, and it seems like this tends to work. And actually, let me finish this one as well. Since the basic operation that we are performing is counting, if it so happens that we have 0 counts for certain combinations, doesn't mean that the probability should be 0. So for example, if you never observe temperature is cold when the tennis is yes, that should not mean that the probability of tennis, temperature is cold given tennis is yes, should be 0. And there's like a giant body of work on the solution to this problem. It's broadly falls under the umbrella of smoothing, where effectively what you can do, the simplest form of smoothing, is you add fake counts. You start off with the assumption that you have seen everything a little bit. So you, instead of starting your counter at 0, you can start your counter at epsilon, so that you never end up with zeros. Some small numbers. Instead of starting all the counts at 0, you can start all counts at some small number, and that will basically solve the problem. That is called Laplace smoothing. The more general way of solving this problem is to think of map learning, which basically acts as priors. We won't have time for this, and this is a big enough body of work that I don't think we'll have time to cover this even in another lecture, but just if you need to learn a naive-based classifier, you should always do smoothing. If you don't do smoothing, you'll end up with zeros in your probabilities, and because we are multiplying these quantities, you'll end up with zeros in the predictions as well, which basically ruins all math. Alright, we should stop now. Have a good Thanksgiving. We won't have class obviously on Thursday. But do take a look at the homework. I think you should, I encourage you to go ahead and come back to me with questions and stuff. And I have office hours now.